So, hello, good morning, everybody. So, today we are going to talk about what are neural networks. So, I'm going to cover all the basics in this video. This is going to both be a theory lesson and also a hands-on tutorial of what you learn over here. And uh, for the theory part, I expect you to not just learn from what I'm teaching here. Um, I actually wrote this article and I will be referring to this article throughout this video to teach you. And I also expect you to go through the whole article if you want to actually learn the whole gist of neural networks. All right. So, what are neural networks? In short, neural networks or deep neural networks or artificial neural networks, whatever you may call it, they are basically the building blocks of any type of AI, any type of machine learning model. The be it ChatGPT, be it self-driving cars like Tesla or anything, the building block, the core thing is nothing but neural networks. So, what are they? If they are so foundational and if they are so important, what are they actually? So, basically, neural networks is a type of architecture used in ML models, and it's actually inspired from what our human brain looks like. Uh, if you just search here, human brain network, all right. So just go to the images section. You see something like this structure, right? If I just zoom this image, maybe show you. So you see this, there's these points, the multiple points, the thousands, maybe millions or maybe billions of them. And they're somewhat interconnected, all right, through. So there's this kind of like spider web-like structure in the brain. And if you just look at any kind of neural network, so this is a very simple kind of neural network, but if you look at neural networks of much larger applications, they would look something like this or even more complex than this. So neural networks are nothing but abstraction of what our brain actually works like. So they mimic basically how our brain thinks, how our brain learns from the experiences we humans have, and that's actually used to make the ML model learn from the experiences, from the data set to be more technical. All right. So neural networks are nothing but they're this uh, simple, not simple actually, they are this complicated web-like structure of these points that you can see on the screen. And these points are known as neurons. All right. So you must have heard of the word neurons, right? If you just search neurons in human brain. So neurons basically, what are they? Neurons are nothing but they help to transfer message, transfer any sort of message between different parts of the brain, different parts of the body. All right. And there are billions and billions of neurons in our brain. To be precise, there's around 86 billion neurons in our body, in our brain. And the neurons in a neural network also somewhat work like what they work like in the brain. All right. So they help to transfer information between any two points. All right. They help to just transfer the information or to just store some information. All right. So just for the basics, you can just remember that. And if you want to learn more about, like, I've basically wrote, just like I said, what neurons are. You can just think of them as variables that contain some numeric value. All right. So if you just go down below here, so neurons are basically, you can think of them like boxes which contain something inside them. And when required, you can fetch, you can just basically open that box and get that thing inside that box and do whatever you need with that object. So neurons are for that purpose. And there are billions of neurons in a neural network. But the neural network today we are going to build, it's not that complicated. There's just going to be maybe 100,000 neurons in the neural network. All right. So uh, that's what a neural network is. Move on to what you see over here. So this is a neuron, this is a neuron, all these are neurons. And neurons are basically divided into layers. So each layer basically tells us which type of neuron is that. Like it helps us to associate the neuron with some kind of uh, classification. So for the input layer, basically the input layer means that these are the neurons that's basically uh, into which you fed the value for the ML model to be trained. All right. So these are the places where you actually fit in the value, where you actually put in the value, right? You must be knowing that without data, an ML model cannot be trained. So you need to feed that data to the ML model. So where do you feed that? You feed it into the input layer. Then there comes the hidden layers. So they're also known as middle layers, and they're also known as hidden layers. Middle layers because they are between input and output. Output layer is nothing but the layer where the actual output comes. Right. We'll discuss about it in just a few minutes. But middle layer is between the two of those. All right. And they're also known as hidden layers due to the fact that the processing basically happens there. The main processing of the neural network, all the learning, all the crazy magic that you see in a neural network happens inside those layers. And they are known as hidden because there are in a very like complicated neural network in a real world ML model, there will be billions and billions of hidden layers. So as a person who creates the ML model, you can't actually keep record of what those layers are doing. After a point, they just behave in ways that can't be predicted by the creator itself. So that's why they're known as hidden layers. There's something hidden to them. There's something that's hidden from the naked eyes. All right. So that's the three kind of ways. Yeah, I'm actually moving on to the output layer. That's basically where you get the output. All right. So let's just think of a ML model like, let's say you want to build an ML model, uh, which basically into which you just uh, fetch in a photo of uh, a dog or a cat, and it just tells you if it's a dog or a cat. So the image of the dog or the cat will be fed into the input layer. And then the processing happens in the hidden layers or the middle layers. And then basically the output layer will be will be providing what all outputs you are expecting. So it might output that the image is of a cat or a dog, depends on the image. All right. So that's the three kind of layers in a neural network and how the neurons are basically divided into. All right. So if you move on to what are weights and biases. All right. So just like I said, that a neural network is made of thousands and billions of neurons. And neurons, you can think of them as variables that store values. But just storing values doesn't help. All right. Just storing values is somewhat of a database, you can say. But we're not building a database. We want to build an ML model that can learn from data. So how do we do that? So we use something known as weights and biases. So weights and biases help us to basically uh, take that data, all right, take that data inside each of those neurons and bring some life into them. So how do that do that? So let's say this is the input layer, and these are some random values that I've decided for each of those neurons. And let's say that for for each neuron, there is a weight dedicated or associated to it. All right. So for let's say this first neuron is W1, for the second it's W2, for the third is W3, for the fourth it's W4. And there are also some random values. All right. Uh, so what do they help in? And also this bias thing. All right. A bias is also associated with each neuron. So let's say that for this one it's uh, B. So the bias B is associated with this neuron. So uh, basically, weights and biases help us to calculate the value of a neuron. All right. So why do we need to calculate the value inside a neuron, the value of a neuron? Uh, See, the data is just fed into the input layer. But so let's imagine that this data has been fed into the input layer, but it needs to go from here to here, then from here to here, and then from here to here to produce the output. All right. So it needs to propagate from the input layer to the output layer. And how do it does that? So for the for all the previous neurons, we need to calculate the value of the new neuron. So we calculate the value of this neuron, this neuron, this neuron, this neuron, this neuron, based on the values of the input layer neurons. And then based on the values of this layer, we calculate the values of this layer. And then based on that, we calculate this. All right. So that's why we need to calculate the value of a particular neuron. So how do we do that? So basically, the weights, just to like give you a very simple math equation, it's very simple. So the value for each neuron is calculated as the summation of all the weights multiplied by their respective neurons values basically, and adding the bias at the end. So in simple terms, let's say this is x and I want to calculate what x is. So x is basically it's the summation of, so first you need to basically uh, multiply the weights with the values of the neurons, and then you need to sum those, and then you need to add the bias. That's the value of the neuron, as simple as that. So for the value of x, it's W1 into 0.2 plus W2 into 0.4 plus W3 into 0.8, W4 into 0.1, and at the end plus B. So you know W1, W2, W3, W4, and you know B. So you can calculate the of x from this very easy. And that's how neural networks do so. So from here, you must have got a gist about what weights and biases actually are. Weights are basically magnitudes, they are numbers which decide the importance of any uh, neuron. So let's say the weight of, let's say this W4 is basically 0.1 as we can see here, right? If you can't see, just I'm just zooming it, you can see it's 0.1, all right? And this weight of the third neuron is 0.7. So what can you infer from this? You can infer from this that the third neuron is actually way more important for the network as a whole than the fourth neuron. So that's basically giving some weightage on a particular uh, neuron. So that's why they are known as weights. And biases are nothing, but there's just a, you can think of it like you cook the whole food and then you just sprinkle a little salt on it just to give a last touch. So that's bias. Bias is basically giving a very nice last touch in the network, in the calculation of the neuron. So that's basically what bias is. And that's what basically weights and biases are. All right. And these set of weights and biases, uh, you can see this they're already defined. The values are already defined for these weights and the biases. But in a network, these change very frequently. All right. And why is that? Because the network learns. All right. So let's just take a very simple example. All right. So let's say that you are studying for a exam. All right. And let's say there are 10 topics that you are studying. There are 10 topics that going to come on the exam. And let's say that you study the first three topics and then you give a mock exam. That's basically just like the real exam. So you give that mock exam by studying just the first three chapters. And then let's say that you see that your score is maybe let's say 20 out of 100. Then let's say that you study the next three chapters and then you give the mock test. And then let's say you score maybe 50 and then you study the rest of those chapters. And then maybe let's say you score 80 out of 100. So basically, what's happening with each mock test is that you're identifying the weightage of each chapter. Even while studying for any kind of exam, even for any competitive exam, or even for your class 11, 12, or even in your college exams, you must have studied uh, based on how much weightage the chapter holds. Suppose there's a chapter which holds 50% of the whole marks, 50% of the whole syllabus, 50% of the whole paper, and there's another chapter that holds just, let's say, 10%. So you wouldn't want to waste your last minutes. Let's say you have very few minutes left. So you would want to spend more time on that higher weighted chapter, right? And you would like to spend less time on that less weightage chapter. All right. So you would avoid those things, those chapters. All right. And how do you know which chapters to avoid and which chapters to engage with more? That's basically through weightage. You knew that through weightage. If that weightage had not been given to you, or if you had not been able to calculate that weightage, there would have been no way that you would have understood which chapter uh, should you study more or which chapter you should avoid. So that's how you're learning. That's how you're improving the score of your exam. That's how uh, basically you can say increasing the chances of you scoring higher marks. And that's how basically the neural network also does. That's that's why weights and biases are used in the neural network. They use it to identify which information is more critical, which information can be basically discarded, and it's not like uh, the weights and biases are fixed, as I said. They change it. They are changing based on what the ML model learns. So let's say there's a particular a combination of uh, weights and biases, and the model is performing not that great. So it will maybe change those weights and biases a bit to see if the accuracy goes high. And if the accuracy goes high, the model will most probably adopt those uh, weights and biases and not change them so drastically. All right. It may change them just for seeing that what if I change it and a little bit more accuracy comes along, but not drastically. So that's basically what weights and biases are. All right. Uh, I'm not gonna jump into what gradient descent is right now, but just to give you a gist of what gradient descent is, gradient descent basically, in the mathematical terms, it's basically the slope of a curve. And in terms of a neural network, it basically helps us to, just like I said, that the AI model, the ML model basically selects the best combination of weights and biases. So how does that model do that? That's through gradient descent. All right. And I've wanted to read this article. I want to go through this article fully. It's not that long. It's just a 10-minute read. So you just go through it, and you will. I'm for sure that I'm damn sure that you will easily understand. So stochastic gradient descent also you can go through it. It's also very easy. Uh, we've also covered layers. All right. So what's basically softmax function? If we move on to this diagram, all right. So as you can see, the output layer. So uh, your mind must be questioning that there's just one output that you get from a ML model. All right. Let's take our previous example of the dog or cat one. So there's just one output that you get from the ML model. That is dog or cat. It's the output is either dog or the output is either or it's cat. All right. But at the core, actually, there's not just not just one output. There's actually a collection of outputs, and it depends on how many the type of objects we are classifying the data into. So in our case, there's just two. All right. That's just dog and cat. We are trying to classify the given data into whether it's a dog or a cat. So the number of neurons in our output layer will be two. All right. Let's suppose we are building a model that basically recognizes human written digits. And that's what we are going to build in the practical section also. So what what do you think? What's gonna be the number of neurons in the output layer? So that's gonna be 10. All right. So from 0 to 9, that's 10 digits. All right. So there will be 10 outputs. So for each digit, there is some kind of output that's coming from the ML model, but you are being shown as a user, you are being shown only that one that has the highest chance of being actually the correct output. So how do that model actually does that? That's through a special kind of function known as softmax function. We'll not go into the deep mathematical implementation of it, but just to understand, softmax function basically helps you to convert all that uh, different outputs into basically probability distributions. So let's take our example of dog or cat. So let's say there's some number that outputted for the cat and there's some number that's been outputted for the dog neuron. So the network is going to take that value and it's just going to convert it into a probability. All right. Let me just show you a bit. So let's say this is the neuron of the dog one, and let's say this is the neuron of the cat one maybe. Right. This is the dog one. Uh, this is the cat one. Right. And let's say there's some number over here. Let's say 0.7 maybe. And let's say there's some number over here. Say maybe 4.2.5 maybe. So there's this special kind of function known as softmax function. Right. Just imagine it's something like this. Right. So this softmax function. All right. So what it does is basically you just feed this into the softmax, and then what it does is that it actually converts it into probability distributions. All right. So let's just draw the dog neuron and then the just a second, the cat neuron. All right. And what it will do is basically it will convert it into some kind of probability. Let's say this is 0.35, and if this is 0.35, so this will be of course 0.65, because there are only two options in our case, right? This is the dog one, and this is the cat. All right. So this is how the softmax function works actually. So there's this output layers. All right. This is the output layer. All right. So this is the output layer, and in our case, it's just dog or cat, and there's some number being uh, that's inside that dog neuron and the cat neuron, and that's just fed into the softmax function, and it just converts it into probabilities. So if we want to see the example of maybe the uh, the example of that digits one, so there will be 10 of those. All right. So one, two, three, four, and lots of them, and then they will be passed to the softmax, and then they will be converted into the probability distributions. All right. So that's basically what softmax is. All right. It's as simple as that. And we'll also see that in action also. All right. So now what's backpropagation is? Backpropagation is nothing but it's the process. Uh, till now what we have discussed, that's what basically backpropagation is. So basically what the AI model does is that first it feeds the data forward. All right. So what does feeds the data forward mean? So feeds the data forward is basically, let's just go here. It's basically feeding the data forward towards the output layer from the input layer. All right. Then what happens is that basically, how does it do that? It uses what? It uses basically the weights and biases, right? Just like we learned, the weights and biases are used to basically uh, feed the feed the data forward in the neural network. And then what's going to happen is that basically we check the output, right? We check the output. Let's say, uh, just like in our case, let's say we got the output something like this. So the answer is, let's say cat, right? So we got the output as cat with a probability of 0.65 or 65%. But let's say that our actual, uh, that actual, just a second, that our actual output was, let's say, dog, maybe. So what happened in this case is that the data was fed forward and then the output layer was calculated, softmax was applied, blah blah blah, and then the output was calculated and it was cat. The answer was cat. But the actual correct answer was dog. So the ML model must have gone somewhere wrong. So how do it basically correct those mistakes? That's basically going to the weights and biases and changing them. All right, changing the weights and biases. Just a second. Yeah. So that's how the a model basically sees where it went wrong and it basically adjusts the weights and biases to see if the uh, next time the output is actually dog or not. And then this whole cycle continues. All right. So this whole cycle continues. All right. And this is basically what's basically back propagation known as. So what happens is that first your data moves in the forward direction. All right. You get the output and then you actually reflect on that output. Like you must have heard from people that you should reflect on yourself to become a better person. So, ML model also reflects on its outputs, and then makes itself better. So it sees where it went wrong. So it will see the output and compare it with the actual correct output, and then it will see maybe let's see if we went wrong here. Oh no, let's see over here. Oh no. All right. So it will basically arrange the weights over here, maybe the weights over here, maybe. That just depends on the network only. And then it will come over here, and then once again the data will feed forward. Okay. And then once again back propagation will occur. And this will occur till the time a very, not a very, but a sufficient amount of accuracy is achieved through the model. So how? So this whole process, all right, this whole process of basically first feed forward and then back propagation, this one cycle is known as epoch. All right. So that's what I was gonna teach you next. Just a second. Yeah, after back propagation, that was epoch. All right. So that's what basically epoch means. So basically, feed forward is like going this, and back propagation is going this. Feed forward is basically you are uh, basically receiving the instructions from your boss to do the task, and you just uh, try to do that task and then submit the report to your boss. And then you reflect on the feedback given by the boss to you, and then you improve yourself. And then the next time the boss gives you instructions, he will get much better results from you. That's basically how the ML model works. All right. So the theory part's been covered. So now we will go into the uh, practical part. We'll build a very basic neural network. So it's going to teach you the very basics of the neural network, uh, all the concepts that we just covered now. So let's get into it. So hello, welcome back. So now we are going to the practical part. So for that, we are going to use Jupyter Lab. So for that, you're going to need the Anaconda Navigator. So if you don't know what Anaconda is, it's where you can basically download it. Just search Anaconda, download for Windows or whatever your or platform is, and then just click over here, and then just skip registration, and then just choose whatever your platform is. Right. So then you're gonna follow the steps to download Anaconda, and then just search Anaconda, and then just open this. Right. So you'll be welcome to this screen. And then you must be able to find this Jupyter Lab option. So just click on the launch. It's going to take just a few seconds to launch, and it's going to launch in your browser. All right, it's been launched, and you're going to see a screen like this. All right. So right now I want to not click on any of this because uh, I don't uh, I want to make this suitable for every beginner out there. So if you're not familiar with Jupyter Lab or Jupyter notebooks, it will be not a problem. I'm not going to, I'm going to provide you everything from scratch. So uh, I will be providing you this Python notebook. All right. It contains everything. All right. All the code that we are going to uh, see today. And just for the heads up, we're not going to code long. So to keep the video short and for better, and quick understanding, which I'm just going to go through the code and show you how it works. And one quick tip, if you're a beginner, you want to just go and click this. It does not does much, but it basically makes the UI look simpler for you. And if this is the first time that you're using Jupyter Notebook, then it must be that you'll not be able to see this dark theme. So you could maybe just go and select theme, and then just select the Jupyter dark one. And whatever more settings you want, you can do those. All right. So first of all, I'm just going to clear all the outputs of all the cells. All right. So first of all, uh, just to set the context for you, uh, this is going to be uh, a neural network, but it's going to also involve very few concepts of convolutional neural network. And if you haven't like, if you don't know what's convolutional neural network is, I will also provide a video that I made recently. You can watch that. All right. Moving on to the moving on to our today's code. All right. So first of all, we're going to install and set up the required packages, require all the packages that are required for the functioning of our neural network, of our ML model. So what you need to do is that just click inside this code block, and then just you could maybe just click over here this run button, or another thing that you could do is basically just type or just click shift plus enter. So it's going to install everything on your machine. Yeah. And when you just see this message that all the required packages have been installed, you just know that they have been installed safely. And uh, if you're just using this for the first time, you might also be want be given the option to select the kernel for this notebook. So just select this one, this exact one. All right. Don't select any other. All right. Just select this one. Right. So moving on to the next step. So the next step is that we're going to basically implement the basic setup. So basic setup includes that we basically load the data that we need for the ML model. All right. So before loading the data, I'm just going to show you what our data looks like. Even you can search it. Just search it. TensorFlow data sets MNIST. All right. And then just click on the toppest link. Just go down here, Just go down. So this is what our data looks like, data set looks like, right? So just go here. You can see some more examples. I think there's much provided. Or I just stick with this up here. So basically, this data set contains of how many? In total, 70,000, basically it's 70,000 images of handwritten digits. And what we are going to build in our today's video is that we're going to create an ML model that will recognize this as 0, this is 1, this is 8, this is 7, this is 2, and so on. So we're going to basically make an ML model that's going to recognize handwritten digits. And this is the dataset that we are going to use. So it has 70,000 images, as I said. I'm going to speak about this a little after. So before that, what's this TensorFlow dataset? So basically, TensorFlow is basically it's a Python package created by Google, and it's a deep learning package. All right. Uh, Basically, to build a neural network, you need to figure out a lot of math behind it. So TensorFlow helps in doing so. Uh, just a heads up that in this tutorial, we're building a neural network, but we're not actually building it from the scratch, not from the like uh, very scratch. Like the scratch would be like building it using just NumPy and just using equations and stuff. But TensorFlow handles that for you. It makes you writing code for creating these kind of models very easy. So that's why we are going to use TensorFlow in today's video. And TensorFlow has a lot of uh, basically already pre-existing uh, data sets that you can use. And one of them is this MNIST. All right. So basically, this can, as I said, I've already given an introduction of the data set. All right. So now what we're doing here is basically we are setting the data set. We are basically loading the data set into a local machine. All right. So before doing that, uh, I'm going to explain to you what this split means. This test train split, what it actually means is that basically for the purpose of training the ML model, there are 60,000 pictures or 60,000 examples. And for the purpose of testing the model, there are 10,000 examples. By training, I mean basically the model starts from scratch. All right, it does not know anything about those uh, anything about that data set, so it cannot actually recognize anything. So we train that on those 60,000 examples, and it maybe achieves some accuracy in achieving those in basically recognizing those digits, and then we use those rest of the 10,000 examples to basically test whether our ML model has been correctly made or not. That's how we do it. All right. So that's what the test train split means. And here you must be seeing that there's this X train, there's this Y train, there's this X test, there's this Y test, and then we're using this MNIST load data. So just to make this simpler, let's just break it down. All right. So let's say that there's this one image, and let's say there's written like 1, and there's let's say another image, and on it let's say it's written 8, and let's say there's another image, All right. And let's say on its written, let's say 5. Let me make that, let's say 4. All right. So these are the images that we get uh, in this data set. Another thing that we get from with each of the image is something known as label. All right, label. You must be knowing what label is. All right. Uh, as a child, you used to put labels on your notebooks just to recognize which subjects notebooks were they were. So labels are nothing but they actually help us to recognize things. All right, or maybe remember things. So with each image, there comes a label that basically states what this actual number is. So for this one, it's 1. For this, just a second. For this one, it's 1. For this one, it's 8. For this one, it's 4. All right. So these are the labels. All right. These are the labels that you get. All right. This one is a label. This one is a label. This one is a label. So what label helps us to do is that just like in the previous example that when I was talking about the theory part, I said that the data is first fed forward in the neural network through the weights and biases. Then it compares with the correct output or the actual output, and then it basically changes the weights and biases. So the actual output or the correct output is what is basically represented by the label. The label is what the actual output or the correct output is. So with each image, we sort of get that this is the correct one. So for each image is it's like that we feed this into the network and we say that you try to recognize this image and your answer should be 1. It should not be any other number. You try to recognize this and your answer should be 8 and not any other number. And the same for this one. So that's how the training is done. So this X train and this Y train is basically, first of all, let's just understand what's this train and this test is. We already understood that this, uh, where is it? Yeah, the training data is around 60,000 images. The testing data is around 10,000 images. So this training, this these variables actually store the training data and these variables actually show the testing data. So what's the X and the Y? This X is basically the actual images. Let me just write it over. So this is X and this is Y. All right, just a second. All right. So X is basically the images. All right. And Y are basically the labels. So X train is basically all the images of the training data set. And Y train basically means all the labels of the training data set. And the same for the X test and Y test. And this basically helps us to load the data. Then what we are doing is that we are basically doing something known as normalizing the pixel values. So what is it? So basically you must be knowing that whatever type of color there is, all right, there must be some red, green, whatever color or it is, it's always denoted from a value of 0, just a second, from value of 0 to a value of 255. You must be knowing this, or if you did not, this basically each and every color, the intensity of the color is basically given a number between 0 to 255. All right. So what does this, what's actually happening in this is basically, let's say there is this image of, let me draw something. Let's say there is this man over here. All right. So let's say this is a image. All right. So how does this basically neural network will process this? It cannot actually see this image like we humans do. All right. What it does is actually it breaks it into pixels. All right. It breaks it into pixels. So it breaks it into something like this. All right. Something like this. All right. So this is how the basically the image is broken down into pixels. If you see this box over here, this box over this second, this box over here, all these boxes are nothing but pixels, right? What are these? These are pixels. Pixels are basically a very tiny part of a image. An image is made up of maybe hundreds or thousands or millions of pixels. The more the pixels, the clearer the image is. All right. And each pixel is basically denoted in numbers between 0 to 255. All right. You should know that. Uh, so basically, let's say this, let's say this one. All right. Let's take the example of this pixel. All right. This one right here. And let's take the example of another pixel. Let's take the example of this pixel. All right. So this pixel has some uh, black ink on it. All right. So the pixel value of this might be something like, let's say 125 or 126 maybe. And the pixel value of this one, let's say it's, you, as you can see, it's fully white. So let's say its value is 0. All right. So pixel value basically gives us an idea about how much uh, intensity of light it holds inside that pixel. That's basically what the pixel value denotes. All right. So what we are doing is that basically we are normalizing the pixel values. As you can see, normalized pixel values to be between 0 and 1. So the default pixel values is between 0 to 255. But why do we want it between 0 to 1? Basically, it actually helps if the data is given between 0 to 1 to a neural network instead of very large numbers like 0 to 255. So what we do is that we basically divide this, divide this by how much? We divide this by 255. So what this becomes is that basically it becomes from 0 to how much? 1. So this becomes 0 to 1. And this process is basically known as normalizing. All right. This is basically what normalizing the pixel value means. And as you can see, the X train, that's basically the images, and the X text, that's basically the images of the test data set. What we are doing is that we're taking them, don't worry about this, we're just taking them and we're just dividing it by 255. The same for this one. All right. Uh, don't worry about this right now. But what it actually does is that, just to like give you an uh, so basically the images provided in the data set are 28 by 28 images. So basically that means 28 is the width and 28 is the height. All right. But what 28 by 28 actually means, a number like basically a number like 28 by 28, what basically means is that, sorry, just a second. Basically, there will be 28 into 28. That's how much? That's 784 pixels in total in that image. All right. That's basically what it means. If I just show you any type of image, let's say, uh, yeah, this course certificate image. So if I just hover on it, I can see that its dimension is 1600 into 1190. So if you just multiply this number, you're going to get the amount of pixels that it has in that image. If I do for maybe this one, not this one actually, I don't have anything else. Leave it. So that's basically what this number means. So what we are doing is basically we are flattening the 28 by 8 images to vectors of 784 features. What it basically means is that, let's say that we have a matrix like this. Right. Just a second. So what's the like order of this matrix? What's this? This is 2 by 2, correct? If I want to flatten it, flattening means uh, basically convert it into a row only matrix or a column only matrix. So what's meant by flattening it? So basically, I open up this matrix and make it, let's say, maybe just a row only matrix. So how would it look? It would look basically something like this. One, two. So one, two, three, four. So now what is this? This is basically how much? This is basically a 4 by 1 matrix. All right. So there's four, no, actually, sorry, it's 1 by 4 matrix. There's just one row and there's four columns. Anyways, so this is what basically flattening means. So basically, flattening is basically converting the matrix into basically a row only matrix, a single row matrix. So we want to convert these 28 by 28 images into, we want to flatten them. So if we want to flatten 28 by 28 image, so how many basically row columns in total would there be? So in total there would be this, yeah. So it would be 28 into 28, that's 784. So it's a very long matrix. So we're converting it into that because uh, instead of giving something like this to the neural network, this would be much better. Just to like give you a context, like this is the input layer as you can see, right? Uh, just think about it in very common sense, very intuitively. Can you fit this into this input layer? No, right? But can you fit this into this one, right? Correct. You will fit this one into this one, the second one into the second one, and the rest of the two to the rest of the two. So that's basically how why we are flattening the images. So this basically helps us flatten them. And then we are basically printing the shape. Uh, just a second. There seems to be some kind of error. All right. So just to show you the kernel, I had like basically changed the kernel. So I had to reinstall everything. That's why it was causing problem. Now it should work. Yeah, it's working now. Yeah. So basically, as you can see, there's 60,000 images, and each of those images are 784, or you can think 784 meter long or centimeter long, something like that, just to think of it intuitively. And there's 60,000 such images, or not. Why think of it as centimeter? Just think of it as 784 pixels. And as you can see, the Y train shape is just labels. So there's just 60,000 labels. There's nothing pixels related to those. For the X test shape, there are 10,000 uh, images, and each of those images have 784 pixels. For the Y test shape, that's basically the labels of the testing dataset. So there's just 10,000. All right. So now we have done the basic setup and now we know how it's working. So now let's actually create the neural network. So this this is where we actually are creating the neural network, right? So as you can see, this might be a bit hard to digest, but once you code and make a few ML models in TensorFlow, it will be really easy for you and you will be well versed in this. So basically, we are creating a ML model using the TensorFlow library, and inside that we are using the Keras library, and inside that we are using this particular uh, constructor that's sequential. So sequential, what this basically helps us is it helps us to create this sequence, this kind of neural network that we want. This sequence it helps us to create. And don't worry, we are not going to have four of them. We are just going to have three of them. So see, this one is actually not the first layer. This one is actually a second layer, and this one is actually a third layer. I've also put comments there so you can uh, read them for later uh, reference. So for the second layer, as you can see, uh, basically if you see just if you just see this argument, there's this argument something known as input shape, and that is 784. So basically, just to explain you that, just like I said that we flatten the matrix into something like that so that we can fit it into the input layer. Now we flatten these 28 by 28 images into 784 uh, uh, vector like vectors. So we need 784 neurons in the input layer. So that's how we are defining this. The input shape as 784. All right. And then basically we are uh, basically what we are uh, basically specifying in this is the number of neurons of the hidden layer. So the first one will have 784, then the next one will have 128 neurons. Another concept, as you can see, is this ReLU. So what is ReLU? So just to explain you what ReLU is actually, uh, let's say that there is this equation that you have. Let's say it's x square plus x plus 1 And let's say you apply some mathematics, apply some operation on it, some mathematics. Let's say that what you do is basically you convert the x into x plus 1, maybe something like that, maybe. So what will our equation become like? It will become something like x plus 1 whole square plus x plus 1 plus 1. Is that correct? Now, what I can do is that I can apply uh, further mathematical operations on it, and then maybe I can maybe form a very complex, a very complex mathematical expression. So, what ReLU comes in how does ReLU comes into the picture of this? So, basically, what happens in a neural network is that, as you can see, like the equation that I gave you for the weight and bias for the calculation of the uh, uh, value of a neuron, it's something. It looks something like this, but not actually like this. So let's just say we calculate the value of this, all right, and we use the weights and biases to calculate the value of x. Now let's say we want to calculate the value of this one. So once again, we're using some weights and biases based on these set of neurons, and then we're going to calculate on this. But can you just represent this one in terms of this? I know that you can represent the value of this neuron in terms of these. That is for sure. That's basically through the weights and biases equation. But can you represent the value of this one using this one? Yes, you can. Basically, the you can, for each of the weights and each of the value of the neurons, you can break it down in terms of their previous weights and their previous neurons. All right. So basically, this neuron can be broken down in terms of these. So there's basically what you can infer from this is that the output layer can actually be broken down into the in terms of the input layer. So we don't want something like this in our uh, artificial neural network. Why? Why is that? Because it's actually not learning something. It's not actually helping the ML model to learn something. It's just uh, a very maybe big mathematical equation that's basically manipulating the numbers, but it's actually not helping uh, the ML model learn something. We want to do something different. So what we do is that before passing the values from one layer to the other layer, we apply something known as ReLU. So what ReLU does is that, let's say the value of, let's take this, just a second. All right. So let's say we have x. So whenever the value of x is 0, what it basically does is that it passes 0 or more than 0, or let's me just write it as greater than 0. It passes the number just as it. All right. So if let's say x is let's say 1.2, so it's passed as 1.2. But if the value of x is basically uh, less than, just a second, less than 0. So what it does is that it passes not x but 0, right? So ReLU is this special kind of function, you can say. We also learned a special kind of function known as softmax, and ReLU is also a special kind of function. So what it does is that it takes x, and if it's greater than or greater than 0, it just gives x, and if it's less than 0, it just gives 0. So what this allows us is that it actually helps us to create uh, not just the linearity that we had. It actually helps us to break out of that linearity and actually create some uh, not just some fancy equations, but actually something that helps the ML model learn. So you don't actually need to dive deep into this. I just explain this just for your general knowledge purposes. But uh, in any kind of middle layer that you're building, always do this activation. And for the last layer, the output layer, you're always going to use this one. You're always going to use the softmax as your activation. And why is that? Basically, the softmax, as I mentioned, it basically, just a second, it basically helps you to convert the values into probabilities. All right. So basically, in the just a second, yeah, in the last output layer, we apply the softmax activation. So that's how the output layer is constructed. And if you just ask me this number, so as you had already seen earlier, this number as 128. So what 128 represented is the number of layers that originated from this layer. So this is also the same number. And why is it? Because it's one for each digit from 0 to 9. So that's 10 neurons. We want a neuron for each of the digit in the output layer. So that's why we mentioned there 10. All right. So that's it. That's how you create the model. Then we are basically compiling the model. Right. So basically in compilation, we basically provide a few uh, metrics or a few, or maybe you can say arguments. The first one is basically optimizer. So basically, the whole process that I mentioned to you, this whole this epoch thing, this back propagation, this whole process, this is basically nothing but optimizing the ML model. This is basically nothing but optimizing the ML model, correct? So we have TensorFlow to thank for because we don't need to do all this hectic process on our own. We just use a library from uh, TensorFlow, that is Atom Optimizer, and it does all this for us. And we define another argument, that is the loss. You don't need to know much about this. This basically helps us to know the loss. And loss is basically how much your model is actually deviated from the correct model, the correct answer. And the metrics is basically mentioning accuracy. We want to see the accuracy of the model in each step. All right. And it's going to print the summary of the model. So if you can see, uh, the input layer is actually not mentioned here. The just the middle layer and the output layer is mentioned. So output shape, as you can see, it's 128 and it has 10. The number of parameters is around this. There's also a lot of formulas regarding how the total parameters are calculated. but I'm not going to go into that. You can Google it or maybe use ChatGPT for it. All right. So now our model has been created. So now we are going to train the model. So for that, we are basically using model.fit. All right. So model.fit is basically a special kind of function that basically helps us to train the model. And we are going to store this data in the history just to keep reference for the future. So what we are doing is that we are giving this data. All right. Don't provide the test data over here. Provide the training data. So this is the training image, and these are the training labels. Now, what is this batch size? Batch size is basically, uh, you know, like the ML model does not like take one and then does take just one image and then uh, does this whole process that I mentioned for just one image. It does that for a couple of images. All right. And the number that mentions how many images should be uh, evaluated in this one cycle is basically batch size. So the batch size is 32. So what batch size 32 basically means is that before making any sort of changes in the weights and biases, before making any changes in the model, you need to process at least 32 images, and after that you actually optimize the ML model. That's how basically it works. And as I said, this whole one cycle is known as epoch. So we are doing 5 epochs. And the validation data is this one. So this is basically you provide the basically the test data set over here. And don't worry about this verbose. So let's just run this. So as you can see, it's running the, and as you can see, there's this accuracy thing and this loss. So you can see the accuracy is going up and up. And yeah, our model has been trained successfully. So we gained 97% accuracy and very less loss. 97% accuracy is actually a lot. Okay. So congratulations to you. You just trained your very first ML model. Now let's evaluate the model. So basically what we are doing is that we are now evaluating the model on the test data set to see how it's actually performing. The training has been done. All right. Now we're just evaluating the model. So let's just run this. And as you can see, it's almost the same. It's actually the same. The accuracy that it performed in training and the accuracy that it performed in the evaluation, it's almost same. So that means your model has been correctly uh, trained and it is good to go for future predictions. And that's what we are going to do now. We're going to make predictions with the trained model right now. All right. So we're just taking some sample images from the testing data set. We're just taking 5 of them and the labels for them also. And we're just making predictions for them. Model.predict, we're just going to enter the sample images. And then what this basically this predicted labels does is that it basically, this argmax is basically, uh, it's, you can say it basically, uh, it's somewhat like a sibling of softmax function. Softmax basically uh, converts these into probability, and argmax what basically it does is that it selects the one with the highest probability. That's what argmax does. So from the predictions, we basically select the one with the highest probability. And we do this for all the 5 images, as you can see. And we also plot them. don't worry about this code. This is not actually related to your neural network and all. This is just a simple matplotlib code. You don't need to worry about it. If you want, you can just copy it for all the next projects that you're going to do. But right now, I'm just going to run this and show you. So these are the 5 images that we predicted with our model. As you can see, the true one is 7 and the predicted one is 7, and it's accurate for all of them. Let's try to change this. Let's try with from 5 to 10 maybe. Let's run this. All right. Even now you can see it's done pretty well. Even from my naked eye, I cannot actually recognize if it's actually 5 or not. It's our model has become so accurate that it correctly recognizes this as 5. So that's how accurate our model is now. All right. And a last step would be to basically save this trained model. You don't actually need to do this. You can even run this if you want, or even if you don't want, it's okay. It will basically create just a second. Yeah, all right. So yeah, you have finally created a simple deep neural network from scratch, and the concepts that you have learned over here are a lot. So I want you to go through this article once. It's just 8-minute read. Just give it a read, and I want you to download this code and just play around with it. By play around with it, I want you to go to this website and then just clear this out and go to this one, and then just find the data sets that you are interested in. There are a lot of uh, here. Just second. Yeah, catalog. Yeah, you can see there are a lot of data sets inside the TensorFlow library. You can use any of them and you can build something like this for them also. For that, what you can do is basically, let's say this is some speech recognition stuff. So let's just go here. So what you can do is just see what's a train as there's actually nothing provided for the test here. So you need to do it manually, or let's say scene classification maybe. Mm, this is actually a very big data set. So you can maybe find something that you like, something like text classification maybe. And this one is nice. And this is also less size. So you can maybe use this one to try and create something, and you just play around with this code, and just to like uh, uh, give you a sense of to how to play with this code is that you can try doing something like instead of just three layers in the neural network, how about you add maybe four or maybe five? Just see how much uh, maybe accurate the model becomes. Okay, and maybe you can uh, increase the number of epochs. All right, maybe you can increase the batch size, decrease it. So just play around with the code. The code is all yours, and just see how accurate your model is. And maybe just go here and visit something and create something meaningful from this. All right. So that's it in today's video. So I explained all the basics about neural networks and also a quick practical on how to create a very basic one. So thank you.